Hey, George, you're a scientist.
I'm a chemist, yes.
Right, you're a scientist. So, I've been thinking a lot about like water and not just abstractly, but specifically like you get like water stains on stuff. And this is
hmm
something I'm sensitive to because, like, we grew up in the very humid, god awful subtropics where everything was kind of damp all the time. And now,
Including the people.
especially the people. And now I live out in the Mountain West where, like, you could basically dump a bucket of water on the floor. And by the time you walk around the outside of that building, it's probably dried up, right? And it's kind of nice. But, like, there's water softeners, and then there's, like, spring water that has stuff in it. And then there's, like, distilled water, which I think, like, kills you. It's, like, not good to drink. So, like, what makes water hard? And, like, when you get, like, a nasty stain on something, like, how do you clean it off?
So, darn it, Lions, I'm a chemist, not a water hardness expert. Uh,
That
not
is
a
the least impressive scientific discipline we've heard so far.
right. Yeah, I guess it would be like somebody who specializes this would be like maybe like a water treatment plant manager. But yes, but I'm neither of those two things. But with my very limited knowledge and very limited expertise, I will attempt to opine to this. So, and you touched on some other things too that we can absolutely discuss while we're doing this because I feel like we're really water is not that important. So I really feel like we're only going to talk about it this once.
That's
Um,
probably true. It has very little impact on day to day human life.
it's either none. How much impact does water have on human life? None. No, dude, immense. Oh, well, I knew you wouldn't have asked unless it was very little or a lot. Anyways, but yeah, so let's take a step back. What is hard water?
I mean, I think it has something to do with the amount of crap in it, but I don't know if it's any stuff dissolved into it, if it's the minerals specifically, if it's some other kind of chemical. It's the not water stuff in water, I think.
Right. Because to your point, right, is that, like people say, oh, well, when the water evaporates, it leaves behind a film. It's like, no, the water evaporated. It didn't leave behind nothing. The water's there, right? It's the stuff in the water, right? Which again, it seems like a minor quibble, but it's important, right? So hard water specifically tends to be calcium and magnesium, two things that are abundant in water, but do get left behind. Like in this thing. Now, here's the question though: is when I say calcium and magnesium, either or, like what kind of comes to mind? Like what do you think of when you think of calcium?
Well, bones.
Don't say bones. Don't
Bones.
say, dude. No.
And I guess probably milk. As an American that grew up when we did,
Oh yeah.
there's a lot of like, oh, you need to drink milk because it's got calcium, which is good for your bones.
Right. Exactly. Right. So you think calcium, good for your bones, right? When you think calcium, do you think explosive in water?
No.
And yet it is. And this kind of comes back to something that we've talked about briefly before, but like the state of the thing matters, right? So, if you look at a periodic table, right, we've talked about sodium, right, being explosive in water, right, and turning the water alkaline, right, like violently ripping hydrogens off of water to sate its need for an octet, right, and then leaving behind the wretched OH molecules to flit around and be dumb, right? Uh, so so sodium does that because it is one away from like an octet, right? So basically, as you add new protons and by extension electrons to an atom, right? These orbitals kind of fill out, right? And then when you drop down to the next level, you had a whole new different energy shell, right? And molecules are cool, or atoms are cool with that, but what they're even more cool with is jettisoning that thing and getting rid of that whole energy level and dropping down, right? So sodium does that pretty well. The thing that's even more jazzed, so that's a group 1 metal, right? The thing that's even more jazzed to do that are group 2 metals because they have twice as many electrons to give and are very excited about getting rid of them. Magnesium and calcium are both group 2 metals. So if you put them into water, they will violently react, and to the point where they can ignite their own hydrogen that they're giving off and burn in water, right?
There's a lot of important things happening right now, but not the least of people are distracted by explosions, but I don't want to glance over the fact that calcium is technically a metal.
Yes, it
so
is.
Our bones are technically metal.
Well, so our bones are salt, which is worse.
That's
think,
way worse.
Better. I don't know.
That's not cool. I wanted metal bones.
Right? Well, because that's the thing is that if your magnesium as a metal is highly reactive. So like if our bones were made out of that, and last time I checked, there is some water in your body.
Yes,
you know,
we determined previously that it is important.
God, that'd be an awesome way for Full Metal for Edward Elric to like kill you.
Yeah.
It's just to distill out the calcium in your bones into metallic calcium and then just explode you from the inside. Maybe that's actually what Scar's doing. Anyways, that's not the point.
Yeah, there's a bunch of people who were doing explodey stuff. That could have been what they were doing.
But yeah, there's actually a whole bunch of things that, you know, because when you think about metals, typically what you're thinking about are the transition metals, you know? So, you know, like those are your, I almost said technetium. I'm like, nobody thinks of technetium, George, not even a little
That's
bit.
true. That's true. Nobody walking around right now is like, oh man, technetium. Now there's a transition metal.
That's the one. When I think transition metals, I don't think gold, I don't think silver, I don't think iron, I don't think titanium. I think technetium. Yep. I'm just looking at periodic table, and that was just the first one I looked at. I'm like, no, never mind.
Yeah, although that was a good little piece of evidence that you're an actual scientist, because a normal person would have just gone directly to words they recognized, like gold and silver and iron.
Which is interesting in and of itself, because gold and silver and iron, none of those have atomic symbols that even remotely resemble their actual name, right? Because gold is AU, silver is AG, and iron's FE. So it's like, what this table's a mess. God, can you imagine trying to do science with it? So anyways, all of that being said, right, is that but the group 1 and group 2 are metals as well. So lithium, sodium, potassium, those are all metals in their pure state. You don't think of them that way because it is so rare for them to be in that state in nature because they are so reactive, right? So when we talk about calcium and magnesium in drinking water, we're typically talking about their salts, right? So like calcium carbonate, right? Or a similarly bonded thing, which is also why like the calcium carbonate in your body would be potentially considered a salt because it's ionically bonded. So it's like, when you think of the calcium in your bones, you're like, well, it's either organically bonded, or if it's ionically bonded, it's kind of a salt, and that's also kind of weird. So that is actually the stuff that's getting left behind when you see like a white film, because calcium carbonate and magnesium, when it's in its salt form, I forget what salts it tends to form, they tend to leave behind like a white film that then becomes crusty and remains, right? So so salts, when I say salt, right, I said that they are ionically bonded. Do you remember the 3 different types of bonds? Quiz, hot shot.
I think I remember the words. The question will be, do I remember the differences between them? You have what? Ionic bonding.
Yep.
Covalent bonding.
Yep.
And
it was the one you got all salty about because salty. Because you're like, it gets its own bond, and I'm like, well, it does a lot of it, and it's kind of important.
Oh, I do remember getting salty, but I get salty about so many things that
says a lot of us as humans. That like, it's like I can remember feeling righteous indignation.
Yes.
I forget about what.
Yes, I remember feeling feelings, but no facts, which is probably why most of society is the way it is. I will phone a friend.
I'll wait. No, hydrogen bonding.
Oh, that is crap.
Well, I'll forward your opinions along. So one of the most important things to remember is that like attracts like, right? So if you're dealing, so then with ionic, covalent, and hydrogen, which type of bonding do you think that we are witnessing with salts, right, or calcium carbonate, things like that?
Well, I'm gonna say no to hydrogen because there aren't hydrogens present.
Correct.
Okay.
Yep.
I was going to be really angry if if I got screwed twice by the same concept.
Hydrogen's just a name, man. Don't get hung up on it.
Oh, it's an element, but it's also a concept that sometimes happens in these other cases. That would be such a science thing to do.
That'd be like gatekeeping at its finest.
Right. Okay, so we've ruled hydrogen out. I'm going to say that because you described, I think you said the way it is probably present in our bones is ionically bonded. So I'm going to go with ionically bonded.
Correct. And so in ionic bonding, right, the one thing actually gives up electrons and the other atom takes electrons. That's the there will be blood of atoms, right?
Right. It's not sharing. It's taking.
It's not sharing. Yes, it's taking. Covalent is sharing, right? So we're dealing with a situation where things have taken things, right? So you've got those kind of like those salt and those ions kind of about, right? So one of the things that you can kind of think about, right, is that like, okay, what then would be you want to get like to attract like, right? So what are some things you could think of that would be, well, I guess let's take a step back first. Which phase of thing would be the best to try to clean this with? Solid, liquid, gas, or plasma?
Well, plasma, depending on what you consider a successful cleaning.
Right? Yeah. If it's like it's clean in that it does not exist anymore.
Yeah. I feel like the only time you would clean something with a gas is if you could get the thing you were trying to clean to bond to the gas and then like float away. So that doesn't seem like that would work well on salts are crystalline. Is that true? They're not all.
Yeah, they do tend to. They
generally
do tend to form crystals.
Yeah.
Yep.
So yeah, that doesn't seem like you would want a bunch of heavy metals floating around in the air. In fact, I think I remember we specifically said that is not a good thing on another discussion. So gas seems like it's out. A liquid would maybe work if it was something that would chemically react with the salt, and then a solid is more like how I would imagine abrasion. Like you're not breaking the thing down chemically, you are like physically removing it from the surface it's on. So
yep.
I could imagine doing either of those, but if it was like a dishwasher, then I would want like a liquid, like some kind of thing to like break it down chemically. Whereas if it was like on the counter, then maybe I would just scrub it off with a brush.
Right, exactly. So you pretty much hit the nail on the head, right? Is that like if you're using a solid, right, then you're basically physically you've delved away from chemistry and more into physics, right? Where it's like I will apply enough force and that will dislodge this thing from where it's at, right? If you're using liquid, then you might be using chemistry, right? And to your point, one of the reasons why cleaning hard water stains doesn't work when you put it in the dishwasher is that if you've got a hard water problem, then
wait a minute.
Hey, what if I cleaned this hard water with hard water? Wait, hang on.
Now you're back to bashing the stains off by colliding other crystals against it.
So let's assume then that we are talking about so what you would typically use is a combination, right? Is that if you can as with all good things, right, is that you doing one thing is great, doing two or more things is better, and that's true for
always,
all things.
Yes,
so,
always, yes.
So the question is, you can just sit there and like with like steel wool or something like that, try to abrasively clean it off. But if you can kind of chemically loosen it up first, right, that'd be kind of neat. So with that in mind, and the idea that it is ionic, what are some household things that you could think of that you might use to clean hard water?
I mean, the first, whenever I think of a cleaner, I generally think of something that's like mildly acidic, because I'm trying to, I mean, I don't generally walk around thinking about it this way, but I'm trying to break down the chemical bonds in the thing, right? I have stuff, right. I want it to not be that stuff so that it is easy for me to remove from the surface or whatever. So yeah,
Yep.
like I would, like a household cleaner might be something like citric acid, right? Or like
Yep.
something like that, something mildly acidic.
Absolutely, right? Why not heavily acidic?
I mean,
Other than the fact that you're unlikely to just have it laying around the house.
yeah, well, no, I do. I mean, it's safe. I tell my kids not to go in those cupboards. I would think because
Wait,
if it's
are you messing with me? What strong acids do you have in your house?
see, that's how I know like I can still nail a straight man delivery because after several decades of friendship, you're like, wait, I think he might actually have acids around.
I was like 90% sure that you were messing with me, but that 10%, if you had strong acids around, like I needed to address that, like it's like I'm pretty sure he's joking, but on the off chance he's serious, I need to know what he's got in his house and like tell him to dispose of.
Yeah, no, we're safe here and boring, I guess. I would again, like on a macro level, I wouldn't want to use too strong of an acid because I wouldn't want to damage the thing I'm cleaning, right? So like if I have a solid surface countertop or a desk, a toy, something that like cleaning the thing means not destroying the thing or stripping the paint off or the coating or whatever. Like the acid, if it's too strong, may also react with the thing. And then if you destroy the thing, why not have just used plasma?
Yeah, and so interestingly, so the thing that you're cleaning matters, right? So if let's just say you got a kid's plastic toy and they left it in water until it evaporated and now it's got hard water all over it, you could use a fairly strong acid on that plastic toy because acids and plastics get along just fine, right?
I guess I would mostly be concerned about the coating, right? The paint, whatever's on the outside, like that leaching off.
Yeah, and I don't know, like with most paints, how that would work. But I think if I remember correctly, most paints are organic, so it would be relatively okay. But again, yeah, right. In case you had stronger acids lying around, but you would still, if you're dealing with a plastic, you would still want to go ahead and use an acid because why not, right? Because again, like acid's not going to do anything to the plastic because plastics are all covalently bonded, right? Now, if you're dealing with metal fixtures, right? The problem is that what you have with a metal is you have a whole bunch of atoms that are all sitting next to each other and they are just super chill, right? And they actually have a different type of bonding called metallic bonding, right? Which is a little different, but more so metallic bonding is if like ionic bonding is late stage capitalism, right? And covalent bonding is like, mid stage capitalism because there's some sharing, some of it's uneven, sometimes it's pretty even. Yeah, it's pretty cool. Metallic bonding is straight up communism, right? Like they're all side by side and they all just have this like massive electron cloud, which is electrons. Nobody cares. Nobody owns anything. Like everybody's just sharing electrons, which is also what makes them great conductors because electrons pass across their clouds super easy, right? Because of all of those electrons that are just so super awesome and chill, an acid would love to get its hands on those. As a proton donor, it would love to get its hands on those electrons, right? So you don't want to use too strong of an acid because then it would start to eat the metal. Now, to your point, and to the point that we said before on what makes stainless steel stainless, right, is that it is somewhat acid resistant and somewhat self-healing, right? So the upside of most of your stainless steel fixtures is they can handle a weak acid. Now, what you wouldn't want to use is something that's organic. So, for example, if you had like paraffin wax that had gotten into something, right, and you were to use a ammonia-based household cleaner, right, it's not going to do a lot because it's organic and you're hitting it with an acid. It's more likely to destroy whatever you've touched it to, right? In that situation, you'd want to use something that's organic. Like if you wanted to dissolve it, what you could do is just put it in olive oil and then it'll rub right off, right? Because the olive oil is organic and it works to dissolve the thing. It's also, while I'm on that tangent, have you ever seen the trick where it's like if you have a dry erase board and the ink has gotten dry on it, right? You wouldn't hit that with ammonia, right? That's going to strip the coating of the board, right? But have you seen people who like scribble on it and then they can like scribble over it?
Yeah. You like draw over the whole thing and then it just wipe it off, kind of thing.
Yep.
Yeah.
Do you know why that works?
I'm gonna guess for that same reason.
Yeah, it's basically so you because you're using an organic compound, you're pushing. So it's got all these dried inks. You're then pushing them back into the solution of this like marker compound, and then you can wipe it all off, right? So in this case, since you're dealing with an ionic compound, you would want to use something that is great at pulling apart ionic bonds, which would be an acid in this case, right? So you got it, right? Anything that's lightly acidic, not so acidic that it's going to destroy the fixture itself, right? Since a lot of times you see hard water stains on things, like metal, like, pipes, your faucets, things like that. Now, if it's glass, you could go full ham, right?
Yeah, go hog.
But yeah, so basically, anything that has like either ammonia based, vinegar is also good. If you're being super lazy and you've got hard water stains on your cups, you can just fill them with vinegar and walk away, and it'll all just kind of like dissolve out, and then you just dump it out. So yes, anything that is lightly acidic for those reasons.
So bonus round question. Where I live, I have super hard water. Do you happen to know? Do you have hard water where you live?
Oh yeah. No. Yeah. One of the things that brought this question to mind is I had this nice clean glass that was just recently nice and clean because we had a hard water problem because I forgot to fill the water softener, and it got to the point where I was like, I can't deal with this. This is obnoxious.
Yeah. So the home that I live in did not come with a water softener. I chose to install one years after living here because one of the cheaper fixtures in my bathroom, and I obviously don't know its exact metal composition, but it appeared from the outside to be like a stainless steel with some kind of finish, like a cheap typical bathroom faucet. The minerals that collected on it destroyed it, like ate through the metal to the point where the entire fixture had to be replaced, which brings me to my bonus round question. What is happening there? Like, why does the salt not just pile up on the outside? What is happening where whatever minerals are in the water, probably calcium and magnesium, are eventually eroding the metal to the point where it collapses?
Well, so as we kind of mentioned, right, calcium and magnesium, right, are ionically bonded, but and let me know if this doesn't directly answer your question. But as I've mentioned before, is that chemistry, physics are heartless, right? They don't care about it, and I don't know why I find both like just calm and solace in that, where it's just like they are just going to do the easiest thing possible, and we've just kind of built society, our brain chemistry, everything off of the fact that it's like this is the easiest like path of least resistance, but give it something else, right? So like calcium carbonate, right, let's just say, right, is given enough energy, given enough the correct chemical conditions, it'll exchange with a different type of iron, say like oxidized iron, right, a different type of ion, for example, oxidized iron, right? So iron oxide is an ion, right, just like carbonate is an ion, right? So given the right conditions, calcium would just say, "Oh yeah, sure, I'll take one of those. Yes, please and thank you." And then it'll start eroding other things. So anything that can ostensibly be ionized would be at risk to be oxidized from calcium or magnesium. Which is why, like again, if possible, if like things could be coated in plastic, which do not ionize, that's the ideal. But anytime when you have anything that's could form an ion, or anything that you would think of, oh, that might rust, it's subject to oxidation.
There's an old, I can't remember if it's from like Bruce Lee or the Tao Te Ching or some ancient wisdom kind of thing that you read like off a greeting card or a fortune cookie, but it essentially amounts to like water always wins. given enough time and patience, water beats stone, water beats metal, water wins, right? Water is maybe second just to entropy in the eventually I'll win the war of attrition.
Well, yeah, and that's the thing, is because water tends to be liquid, right? And it is also lightly polar, right? It has a dipole moment. Like there is all sorts of different just crazy stuff it can do, and also again because it is not worried about timescales. It's just doing its thing, right? So it's just like, oh, for example, when it's like washing away like a rock, right? It's doing one of two things. It's either mechanically eroding it, in which case then it's Like, out of all of the water molecules that have the kinetic energy to check that rock, one of them eventually has just enough kinetic energy to dislodge an atom, right? And neat. But as T goes to infinity, that rock will eventually lose because there is effectively an infinite amount of water, right? Or water also tends to just be great at dissolving things, for better or for worse. So like water is great at like having other stuff in it, like even and we've talked about it briefly on the channel before, but like when all of a sudden if you release a bunch of sulfur into the atmosphere, let's say by burning coal, which tends to have sulfur in it, right? Then that sulfur goes up into the air and bonds with oxygen to form sulfate, right? Which is acidic, and then but sulfate dissolves super nicely in water, and the water is just happy to have it, right? And then it just carries that sulfate everywhere, and then people are like, hey, how come all of our statues are melting? And also I am tending to get sick from all of this sulfate in me. And it's like, oh, well, because the water does not give a crap.
So maybe if we keep burning enough coal, then eventually I'll get to ask you, why does everything have sulfur water stains on it?
Yeah,
Yay.
There you go. You know what? If eventually we keep burning enough coal, we won't have to worry about the podcast anymore.
I gotta go think of a bunch of questions to ask you before we run out of time.